Okay, welcome to the review of acids, bases, and pH. This is going to correspond to roughly the third unit in Chemistry 2. I'm not too sure how your class is arranged, but at some point you're probably going to go over these topics. I'm basing this off of what I've learned in my classroom, and since it's all kind of standard, hopefully it's all relative to the same thing. So we're going to cover acids, bases, and pH. We're going to do some practice problems. First, I'm going to give a little bit of a mini lesson beforehand, just so we can all start on the same level. Okay. Um, so we're going to start off with the definitions of an acid. There are three definitions of an acid, but for this topic, we're only going to focus on the Arrhenius acid and base and the Bronsted-Lowry base. So in the Arrhenius acid and base, when the acid is dissolved in water, it increases the concentration of hydrogen ions. So it increases the concentration of protons. Then in the Arrhenius base, the substance when dissolved in water, it increases the concentration of hydroxide ions. So that's going to be the OH negative. The next definition is Bronsted-Lowry acid and base. So in the Bronsted-Lowry acid, it works as a protein donor. This is going to be our main definition and the thing that we refer to when we're thinking about definitions of acid and bases. So always think that the acid works as a protein donor. And since it's giving off a protein donor, that would be a positive charge, it becomes more negative because it's giving out a positive. They must also have a removable acidic proton. So some examples of acids would be the HCl, H2O, which is water, and H2SO4. So when you look at these, you're going to think proton donor. So if we look at HCl, it would donate the H, the hydrogen, and it would become just Cl minus. Next, we have the Bronsted-Lowry base. It is kind of the opposite of the Bronsted-Lowry acid. It works as a proton acceptor, so it becomes more positive charge. So think about if you have the base NaOH, right? You're going to get another H, so it becomes more positive in charge. So they also must have a pair of non-bonding electrons. And when you think about Bronsted-Lowry acids and bases, you always want to think that they come in pairs. So a Bronsted-Lowry acid must be paired with a Bronsted-Lowry base. Now, if a substance can be either an acid or a base, it is called amphiprotic/amphoteric. Those terms are used interchangeably. Some main examples are HCO3 minus, HCO4 minus, and a main one is water, H2O. So when we're looking at conjugate acids and bases, we're looking at the Bronsted-Lowry, how they come in pairs. So reactions between acids and bases will always yield their conjugate bases and acids. So if we look at this example, HNO2 is going to work as our acid, H2O is going to work as our base. We know that HNO2 is our acid because we know that this is a strong acid, and we'll get into that later. So now that we know this is the acid and this is the base, we're going to look at our products. And you can see, since this works as an acid, it's going to be a proton donor. So then it's going to be NO2 minus. And you can see that this is the conjugate base. So when we're thinking about acids, we're going to think conjugate base. And now we're looking at H2O, which works as the base. So the base is going to add a hydrogen and become H3O plus, which is going to be our conjugate acid. So acids turn into conjugate bases, and base turn into conjugate acids. So Next thing is, how do we tell in this sort of equation which one is the acid and which one is the base? So you have to you have to really memorize strong acids. So a lot of the time we use this acronym, BRICLANOSO, or this mnemonic. So strong acids completely dissociate in water. It's going to be HBr, HI, HCl, HClO, HNO, and HSO. These are not including the numbers of each, but those are the letters. And if you have some of these letters, you'll have a strong acid. Now, weak acids only dissociate partially in water. And to tell if something is a weak acid, they just are not part of bricklinoso. They're not a strong acid. So any acid that is not a strong acid is a weak acid. Then we're looking at strong bases. So in the periodic table, group 1 elements, you look at and then you add an HO negative compound. So for example, we have LiOH, NaOH, KOH, CSOH, RbOH. So these are going to be group 1 elements. But we also have barium and strontium and calcium, which are not in group 1, but close. I think that's just something that you have to remember. So in any acid-base reaction, the equilibrium favors the reaction that moves the proton to the stronger base / away from the stronger acid. So going back up, we're going to notice that this is one of our strong acids. So we know that the proton is going to move away from the strong acid. Since this is a strong acid, its conjugate base is going to be weak. Since this is a weak base, this is going to be a strong acid. So the equilibrium favors the reaction that moves the proton to the stronger base and away from the stronger acid. So this is the stronger acid. It's going to move away to the stronger base. Next, we're looking at autoionization of water. In pure water, a few molecules act as bases and a few act as acids. Now we're looking at ion product constant. So that's going to be Kc. When we're looking at how we write the expression for Kc for this specific equation, we're going to put products over reactants. Now, notice that H2O is not placed in the denominator over below the products. That is because H2O is not included because it is a pure substance. And whenever you're writing these sort of expressions, you don't want to include anything that is pure. And that goes for pure liquids and pure solids most of the time. Next, we're looking at the pH scale. pH is equal to the negative log of hydrogen and equal to the negative log of H3O plus. And conversely, H plus is equal to 10 to the negative pH. And very similarly as the POH, where POH is equal to the negative log of the concentration of hydroxide ions. And just like the H plus, OH minus concentration is equal to 10 to the minus POH. Then when you're looking at it, you're going to find pH plus POH is always equal to 14. So based on previous knowledge, we can determine that a base has a pH lower than 7 and an acid has a pH higher than 7. In pure water, Kc is equal to 1.0 times 10 to the negative 14th molar. Therefore, the concentration of H3O plus is equal to 1.0 times 10 to the negative 7 molar. That is because the stoichiometry is 1 to 1. So you're going to do 1.0 times 10 to the negative 14th is equal to x squared. And then x is going to be equal to 1.0 times 10 to the negative 7. So we can also tell that pH is equal to negative log to H3O plus is going to be 7. Next, we're going to look at dissociation constants for the equation HA aqueous plus H2O liquid. It's going to give you A minus aqueous and H3O plus aqueous. What can we tell the equilibrium expression is? So for this one, I'm going to go ahead and grab it. So we want to write, we know the equation is this. Since it's a Ka, because we're looking at acids, so Ka is going to be equal to the concentrations of the reactants. That's going to be A minus and H3O plus over, the products over the reactants. But let's look at this. So H2O is liquid, so we will not include it in the expression. So for now, we're only going to include HA. This is the expression for the equilibrium constant for acid dissociation, Ka. We also look at the greater the value of Ka, the stronger the acid. Now we can do the same thing for Kb. We're going to look at this. So we have our products, Hb, and the concentration of OH minus. And that's going to be over, again, since H2O is in its liquid form, we're going to only include B. Okay. And this equilibrium constant is called the base dissociation constant. So whenever you're working with acids, you're going to look for Ka. And whenever you're working with bases, you're going to look for Kb. And the greater, similarly, just to Ka, the greater the value of Kb, the stronger the base. So that concludes our main notes for this section. I recommend remembering the definitions of the acids and bases, what conjugate acids and bases are, strong acids, strong bases, the definition for autoionization of water. All this information which relates to the pH scale and dissociation constants. And mainly the fact that the greater the Ka, the value of Ka, the stronger the acid, and the greater the value of Kb, the stronger the base. Next, we're going to go into working some problems. And we're going to use all this information to do so. Okay, so for the first problem, we have in the reactions below, identify the acid, the base, the conjugate acid, and the conjugate base. In which direction will each reaction be favored for the reactions A and B? Okay, so we're going to start off with A. I'm just going to go ahead and rewrite it. So we have H3PO4 plus H2O gives us H3O plus H2PO4 minus. So first off, we can tell that this is going to correspond with this, and this is going to correspond with this. So that's what we're going to be comparing. So using our definitions, we know that acids are proton donors. And bases are proton acceptors. So we can look at this H3PO4, and we can look at it. We say H2PO4 minus. So we can tell by comparing these two that we are losing a proton because 3 and 2 is less than 3. So you can put right here, less proton. Now we look at H2O and H3O plus. We can tell that this is gaining a proton. So we can look back at our definitions. We can determine that since the acid is a protein donor, is losing a proton. So we can determine that H3PO4 is acting as our acid, and since H2O is gaining an electron, gaining a proton, it is going to act as our base. Then, looking at the product side, since this is an acid, this is going to be our conjugate base. And then since this is working as our base, this is going to work as our conjugate acid. Okay, now that we have finished that problem, we're going to move on to the next one. I'm just going to get rid of all of this. But I'm going to keep the definitions up just so we can refer to them if we need to. Okay. So, B. Sure. B says H2O plus Cn minus gives us HCN plus OH minus. So first thing we're going to do is we're going to look at which ones relate to each other. So we can see that Cn minus relates to HCN and H2O relates to OH minus. So let's look at H2O first. So H2O turns into OH negative, which means it's losing a proton. Now we can look at Cn minus. It turns into HCN. So it is gaining a proton. Okay. So now referring back to our definitions, we can see that H2O is losing a proton, which means it's technically donating. And we can see that Cn minus is gaining a proton, which means it is accepting. So using this information, we can deduce that since H2O is donating, it is an acid, and Cn is gaining a proton, it is a base. And since we now know these, we can determine that OH minus is going to be our conjugate base, and HCN is going to be our conjugate acid. Now, another thing that this question asks you is, in which direction will each reaction be favored for reactions A and B? For this, you have to use tables, but I'm just going to show you that this equation is going to favor the left side. now I can move on to the next one. Relatively straightforward. Um, you don't have to draw everything out. Kind of using it as an example so you can see, but it is not necessary. And eventually you get to a point where it's not going to be necessary at all. So we can go ahead and try that with letter C. So it's going to be H2SO4 plus Cl minus gives us HCl plus HSO4 minus. So if you want to pause now and try and attempt and do it on yourself, then feel free. I'll give you a second to do that. Okay. If you pause the video, now we can go over and see any mistakes or if you did get it right. Okay, H2SO4 turns into HSO4 minus. We can see by comparing the two that it is losing an electron, meaning it is donating electron, which also means this is an acid. Now, looking at Cl minus, we can see by comparing it that it gains a proton, meaning this is a base. And we can also deduce that this is a conjugate acid, and this is going to be your conjugate base. Straightforward, okay? And just for the sake of the problem, we'll finish off with letter D. So letter D says H2S plus NH2 minus gives us HS minus plus NH3. First, we're going to look at this. So H2S and HS minus, you can see that it's losing a proton. So this is going to be our acid. Comparing this to this, we can see that it is gaining a proton. So this is going to be our base. And finally, we can tell that this is going to be our conjugate base, and this is going to be our conjugate acid. And that's the first problem. So I'll just leave that there. The next problem says, list the common strong acids and bases. What is meant by the leveling effect of water on strong acids and bases? So the first thing we're going to do is list the common strong acids and bases. So we can find out what the strong acids are by using our mnemonic. So it's no. So it's going to be HBr, HCl, HI, HNO, HSO. Now keep in mind, these are just the letters. It doesn't include any numbers. Then we're going to look at strong bases. And we know that strong bases are OH groups plus group 1 in the periodic table plus others. So our main strong bases are going to be LiOH, NaOH, KOH, RbOH, CSOH, COOH2. Sorry, I think that's an A, Ca, because it's calcium. SrOH2. Then I'll put right at the bottom here BaOH2. Now you're going to notice these have OH in parentheses and a 2 below. That's because these, calcium, strontium, and barium, are in group 2. So their charges are going to be +2, +2, and +2. So since OH is -1, we need 2 of those to balance them out. Okay. Write an equation for the ionization of HCN in water. Give an expression for the ionization constant, Ka, for this reaction. So first we have HCN. We know that HCN is going to be our acid because it tells us to find Ka. So we have HCN aqueous plus H2O liquid gives us an unknown. But we do know that this is going to be our acid. So we know that acids donate protons. So we're just going to remove this proton, which is going to be our hydrogen. So by removing that hydrogen, we're going to be left with Cn minus. Then we know that the water is functioning as our base. And we know that bases are hydrogen acceptors. So we're just going to add a hydrogen. So this is going to become H3O plus aqueous. Okay, this is also aqueous, but I forgot to write it. So now what we have to do is give an expression for the ionization constant, Ka. So we know that Ka is equal to the products concentrations over reactants concentrations. Okay, so using this, we know that at the top, we're going to have a concentration of Cn minus and H3O plus. And then at the bottom, we're just going to have HCN. Now, you might be wondering why we did not include the H2O. Remember that when writing constants in this format, we're not going to include pure solids or pure liquids. And H2O in here is going to be a pure liquid. So this is your answer for question 3. So number 4, how does the ionization constant change as the strength of acids increase? So we know that the constant ionization constant is going to be either Ka or Kb. Let me write that again. Kb. If we're talking about strength of acids, we're going to be talking about Ka. Recall that as the strengths of the acid increases, the larger Ka will be. So the answer to this question is that as strength of acid increases, the Ka will increase as well. But if the strength of the acid decreases, the same will happen to Ka. Number 5, write an equation for the reaction of NH3 with water. Give an expression for the ionization constant Kb for this expression, or for this reaction. Now, this question is very similar to what we did up here, except instead of Kb, we're doing Kb, or Ka. Instead of doing Ka, we're doing Kb. So we look at NH3. We know that this is going to be our base. We add water. We know that our water is going to function as our acid, right? So we can tell that the base is going to be gaining an electron, gaining a proton. So it's going to become NH4 plus. And our acid, H2O, is going to be losing a proton. So that is going to become H. Oh, well, we put it instead of putting that. We say OH minus. Now we can go ahead and write the expression for Kb. So it's going to be concentrations of products over concentrations of reactants. So we have the concentration of NH4 and the concentration of OH minus, right up the plus here, over, and just like last time, we're not including the pure liquid, over the concentration of NH3. And that is going to be your answer for giving an expression for the ionization constant, Kb. Okay, so question number 6 says the auto-ionization constant for water, Kw, equilibrium constant for the reaction H2O, gives us H plus OH negative, changes with temperature. Recall at the very beginning that we say that, where'd it go? Here we go. That Kc is equal to 1.0 times 10 to the negative 14th. This is going to be at room temperature, or 25 degrees Celsius. But if we look at this question, we can say that it occurs at 37 degrees Celsius. So it's going to change with the temperature. First thing we have to do to solve this equation is write the equilibrium constant expression for ourselves. So we're going to take 2H2O gives us OH negative plus H3O plus. Again, okay. So this is going to be our equation. Now we're going to write the expression for Kw. So Kw is equal to the concentration of OH minus and concentration of H3O plus. Now, in the problem, it says it increases the Kw to 2.5 times 10 to the negative 14th at 37 degrees Celsius. We want to find out what is the pH. So we need to find out what one concentration of the H3O plus is. So we're going to equal this expression to 2.5 times 10 to the negative 14th. So how do you solve this? For this problem, the unknown is going to be the concentration of OH minus and the concentration of H3O plus minus. When you look at the original problem, you're going to notice that the stoichiometry is 1-to-1. For 1 mole of OH negative, there is 1 mole of H3O plus. So we can deem these as both X times X equals 2.5 times 10 to the negative 14th. You can reduce this equation into saying X squared equals 2.5 times 10 to the negative 14th. By punching that into the calculator, we can find that, the square root of 2.5 times 10 to the negative 14th is going to give us X equals 1.58 times 10 to the negative 7. So now we have the concentration of both OH negative and the H3O plus. Since we want to find the pH, we're going to be focusing on the H3O plus. So how do we find pH? To find pH, we simply have to input this number into negative log. So we're going to take negative log of 1.58 times 10 to the negative 7th, and that is going to give us 6.80. So the pH of neutral water solution at this temperature is going to be 6.80. Notice that this is not the same thing as 7, what we said earlier. And this affirms that it changes with temperature. Okay. The next equation, or the next problem, says determine the hydrogen ion concentration, H plus, in a solution prepared by dissolving 0.01 moles of NaOH in enough water to make 250 milliliters of solution. Okay, so for this problem, we need to know first that hydrogen ion concentration, H plus, times the hydroxide ion concentration is always going to equal 1 times 10 to the negative 14th. Memorize this. So what we want to find is this. But we know that NaOH is a strong acid. So what we're going to do is find the molarity of this to determine this. Okay. So molarity is equal to moles divided by liters. So we're going to take 0.10 moles and divide that by 250 divided by 1,000. We're going to do 0.25 liters. We got the 0.25 liters from the 250 milliliters of solution. And this is going to give us 0.04 molar. So this is going to be our concentration. Going back to this, if we know that H plus is our unknown, because we're trying to determine the hydrogen ion concentration, and that our OH minus concentration is equal to 0.04. And all that equals 1 times 10 to the negative 14th. We plug everything in to determine this. So we're going to divide 1 times 10 to the negative 14th divided by 0.04. And that is going to give us 2.5 times 10 to the negative 13th molar. And this is going to be equal to the hydrogen ion concentration. Okay. Number 8 is a little similar. It says determine the hydroxide ion concentration. So we know it's going to be looking for OH minus in a solution prepared by dissolving 0.52 moles of HClO4 in enough water to make 400 milliliters of solution. So here, we're essentially going to do the same thing, but instead of doing our hydrogen ion concentration, we're going to do hydroxide ion concentration. So first we write out that the hydrogen ion concentration times the hydroxide ion concentration is going to give us 1 times 10 to the negative 14th, just like we placed up here. Now, in a solution prepared by dissolving 0.52 moles of HClO4 in enough water to make 400 milliliters of solution. So we know that this is what we're trying to find. So this is the molarity of these two numbers. To find the molarity, we're going to do the same thing. We're going to divide 0.52 moles by 0.4 liters. Remember that molarity is moles divided by liters. To find liters from 400 milliliters, we just divide this number by 1,000. So now that we have this, we can calculate that to be, it's going to give us 1.3 molar. Okay. Now we do the same thing. We do our hydrogen ion concentration, which is going to be 1.3 molar times X is going to give us 1 times 10 to the negative 14th. To solve for X, all we have to do is divide 1 times 10 to the negative 14th by 1.3. And that is going to give us 7.69 times 10 to the negative 15th molar. And this is going to be equal to the hydroxide ion concentration. Okay, for question 9, it says, what is the hydrogen ion concentration and hydroxide ion concentration of a solution that is 0.25 molar in HBr at 25 degrees Celsius? So we know that HBr is one of our strong acids. And we also know that the hydrogen ion concentration times the hydroxide ion concentrations is going to give us 1 times 10 to the negative 14th. If we have 0.25 molar in HBr, it means we have 0.25 molar in our strong acid. So we're trying to find X. We're going to conduct the same process that we have been doing for the last 3 problems. We're going to divide 1 times 10 to the negative 14th by 0.25. And that's going to give us 4 times 10 to the negative 14th. which is equal to the hydroxide ion concentration. Since we know that the stoichiometry is 1-to-1, then we can also deduce that the hydroxide ion concentration is going to be equal to 0.25 molar. Oh, sorry, that's wrong. Ignore that. So we know that the hydroxide ion concentration is going to be 4 times 10 to the negative 14th. Okay. For number 10, it says indicate how you would prepare 300 milliliters of an aqueous solution of calcium OH2 in which the hydroxide concentration OH negative is equal to 0.0024 molar. First thing we're going to identify is if CaOH2 is a strong base or a strong acid. We know that CaOH2 is one of our group 2 strong bases. The next thing we're going to do is write out the equation. So CaOH2 is going to give us Ca 2 plus 2OH negative. So the stoichiometry here is 1-to-2. So we're going to take the molarity, which is 0.0024 molar, and divide it by 2. Because there are 2 moles of the OH negative. That's going to give us 0.0012 molar. Next, we're trying to find how you prepare 300 milliliters of an aqueous solution. So the next thing we're going to do is multiply this number by 0.300. Remember that it always has to be liters instead of milliliters. This is going to give us our moles, which is going to be 0.00036 moles. Then we find that CaOH2 has a total mass of 74 grams. So we want to find how many grams we need. To do this, we multiply the moles times the grams, and that will give us 0.0267 grams. Sorry, 74 grams per mole. So these two cancel out, leaving us with only grams to give us an answer of 0.0267 grams. Okay, how many grams of the strong acid HClO4 must be combined with water to make 400 milliliters of a solution with a pH of 1.5? We're going to do the same thing we did with the previous problem. We know that HClO4 is a strong acid. Next, we're going to write out the equation. HClO4 is going to give us ClO4 minus plus H plus. Now that we know that, we need to use this information. We know that pH is equal to the negative log of hydrogen ion concentration. And we also know that hydrogen ion concentration is equal to 10 to the negative pH. And we know the pH, so we can determine the concentration. So we do 10 to the negative 1.5, which is going to give us 3.16 times 10 to the negative 2 moles, or molarity. Since we have the molarity now, instead of doing all this to find out the molarity, all this to find out the molarity, now we multiply the molarity by the liters to get 0.01264 moles. Then we identify the moles, the grams per mole for HClO4, which is going to be 100.46 grams per mole. Then to determine the grams needed, you multiply 0.01264 by 100.46. Put moles, grams per mole. And this is going to give us 1.27 grams. Okay. Number 12. Determine the hydrogen ion concentration, the hydroxide ion concentration, and pH of the following solutions. A. 0.02 moles of HCl is diluted with water to a volume of 500 milliliters. So we know that HCl is a strong acid. And we have so far 0.02 moles of it. To determine the hydrogen ion concentration, we need to divide 0.02 by 0.5. This is going to give us 0.04. This is going to be equal to our hydrogen ion concentration. Now, how do we determine what the OH minus concentration or the hydroxide ion concentration? Remember in earlier problems that the hydrogen concentration times the hydroxide ion concentration is equal to 1 times 10 to the negative 14th. And now we know the molarity. So we're going to do the same thing we did previously and take 0.04 times x equals 1 times 10 to the negative 14th. By doing this problem, we can determine that x is equal to 2.5 times 10 to the negative 13th. If you're unclear on how we got to this number, all we did was divide 1 times 10 to the negative 14th by 0.04 to get x. Now that we know the ion concentration of the hydrogen ion, and now we know the concentration of the hydroxide ion concentration. The last thing it asks for is the pH. Recall that pH is equal to the negative log of the hydrogen ion concentration. We know now that the hydrogen ion concentration is 0.04. All we do is in place this number right here. So negative log of 0.04 is equal to 1.39, which checks out because HCl is a strong acid. So we would expect the number to be very low. Let me clear all that up so we can do the other one. Okay. Part B of this question asks 0.6 grams. Notice the difference how this one says moles and this one says grams of NaOH is dissolved in enough water to make 500 milliliters of solution. First, we determine that NaOH is a strong base. And what we have so far is 0.6 grams of it. But we need the molarity. So to determine how many moles we have, we take the grams, place it over 1. All we need is 1 mole. And we know that 1 mole of NaOH is equal roughly to 40 grams. By doing this, we have we're left with 0.015 moles. Now that we've gotten to this step, we can continue with how we did it in part A. We take 0.015 moles and divide it by 0.5. This is going to give us 0.03 molarity. This is equal to the hydroxide ion concentration. Now, to find the hydrogen ion concentration, we do the same thing as before. OH minus times H plus is equal to 1 times 10 to the negative 14th. We know the concentration of the hydroxide ions, 0.03 times X equals 1 times 10 to the negative 14th. To determine X, all we have to do is divide 1 times 10 to the negative 14th by 0.03, which is going to give us 3.33 times 10 to the negative 13th. Now, it also asks to find the pH. pH, like previously stated, is a negative log of the hydrogen ion concentration. Do we know the hydrogen ion concentration? Yes, we just found it. Technically, it's our X. So we just input it, negative log of 3.33 times 10 to the negative 13th. I'm running out of room. But essentially, our pH is going to equal 12.47, which also makes sense because NaOH is a strong base. Now, the last problem in this set says a sample of battery acid has a pH of 0.9. What are the hydrogen ion concentration and hydroxide ion concentrations in this solution? So we know that the pH is 0.9. And we know that pH is equal to the negative log of hydrogen ion concentration. But we also know that H plus our hydrogen ion concentration is equal to 10 to the negative pH. 10 to the negative 0.9 is equal to 0.125 molarity. And this is going to be for the hydrogen ion concentration. Since we know this molarity, we can determine the molarity of the hydroxide ions. So, hydrogen ion concentration times hydroxide ion concentration is equal to 1 times 10 to the negative 14th. We know that our hydrogen ion concentration is 0.125, and we don't know our hydroxide ion concentration. To find x, we divide 1 times 10 to the negative 14th by 0.125, and that gives us 8 times 10 to the negative 14th. So this is the concentration for the hydrogen ion concentration. So this is the concentration for the hydroxide ions. And that's going to be it for this problem set. We're going to continue to build off of this knowledge in the next one.